Okay, good morning. This is Professor David J. Delos Reyes. It's October 11, 2023. The time is 3:28 a.m. Okay, my topic for this session will be continuation of college algebra, and this is now lesson number 87. And the title of the topic will be partial fraction under the subtopic repeated linear factors. Okay, let's proceed. The subject matter will be college algebra, lesson number 87, partial fraction, repeated linear factors. The main reason why I bring out this topic under college algebra is when we reach integral calculus, there are integration process which needs our knowledge of partial fraction. Without knowing our knowledge of partial fraction, we could not integrate. So I will now bring out the second form of linear of partial fractions, and this is under the subtopic repeated linear factors. We are done with the linear factors. We know how to take the equivalent already. So for this morning, I will be discussing on how to take the equivalent partial fraction if the given denominator are actually repeated linear factors. Okay, let's try to bring out the set-up equation. The set-up equation will be of this form here. F1 over x over F2x will be equal to capital letter A with the all over x minus a, capital letter B all over x minus b, plus capital letter C over x minus b. This is to the second power. This is 1, this is 2. And the last term here will be z all over x minus b. The power here is n. Okay? Where the value f2 of x, meaning the denominator on the given partial fraction, is actually equivalent to the product of x minus a times x minus b raised to the n power. If you try to notice it, the first factor is just simply linear. It is not repeated. So why I am giving it? Okay, I included it because I want to include it in the so-called form of repeated linear factor. It doesn't matter. We know already how to take the equivalent partial fraction of this one. The next repeated linear factor is x minus b, and the value n is not specified. So n could take the value 2, 3, 4, and whatever value will be given, right? So for us to visualize the importance of this set-up equation here, okay, I will try to give you an example problem. Find the equivalent partial fraction of the given algebraic expression 3x all over the product of x minus 1 times a quantity x plus 2 quantity square. Okay, let's try to bring out the solution. To bring out the solution of this, we'll be coordinating or we'll be watching the set-up equation, right? So I will rewrite the given algebraic expression, and this should be equal to, I am following the set-up equation, that is a, the first linear factor is x minus 1, it's not repeated, plus capital letter B all over. From the set-up equation, it will be the repeated linear factor. The linear factor is actually x plus 2, right? So it will start with the power 1 plus the value c all over x plus 2 to the second power. So actually, this 2 here is actually the value of n. N is equal to 2. Okay? It could take the value 3, 4, 5, it doesn't matter. But for this given problem, the value of n is equal to 2. So we stop at the value c all over x plus 2 quantity square. Rewriting the given left-hand side, it is this. And this should be equal to, again, I rewrite the given right-hand side. I close it with an open and close bracket. And I will try to multiply this by the value x minus 1 over x plus 2 square all over itself, close bracket. Because actually this total value here is actually 1. Right? I could do this without violating anything under algebra, because if you try to multiply both the left and right by the same number, it doesn't change the value of the given equation. Okay, let's try to simplify. if I will try to expand ABC, I will try to multiply this by this, okay? The multiplier of A that will remain will be x plus 2. Just take note of the value of the numerator. X minus 1 will cancel, right? So what remains as a multiplier for A will be x plus 2 quantity square. For the value B, this x plus 2 cancel with 1 x plus 2 here. So 1 value x plus 2 remain here times x minus 1. So the multiplier of the coefficient B will be x minus 1 times the remaining factor of x plus 2 because the other one was cancelled out already. Plus the value C. If we try to multiply this by the numerator, this x plus 2 quantity square cancel with this. What remains as a multiplier for coefficient C will just be simply x minus 1. Actually, this is all over the quantity x minus 1 times x plus 2 quantity square. Even the left hand side, this is x minus 1 times x plus 2 quantity square. The operation here is multiplication. So actually we can cancel x minus 1. We can cancel x plus 2 quantity square. Right? We are free to cancel. Okay, there is no addition or subtraction in between. Right? As long as the operation is multiplication, we can cancel. So what remains will just be simply 3x. Okay? Equal to A times x plus 2 quantity square plus B times the product of x minus 1 x plus 2 plus the value C times the quantity x minus 1. Okay, I will try to erase again this one so we could visualize what is happening, right? I just show you the cancellation so you will not say I put a magic, right? I expedite a little bit. So I will try to close this one with the green marker. Okay, because we need this equation in the computation of the value of A and B. Okay, okay, let's proceed. There are three unknowns, right? A, B, C. So to compute for the value of A, B, C, it's either that we brought out three equations involving A, B, C. Then we try to solve the value of A, B, C either by substitution or elimination or by determinants. But that's a complicated process. So what we will do for this morning will be the one we used from the previous discussion. That is, we assume a certain value so we could eliminate the other two and we could compute for the first one. So when x is equal to negative 2, okay, this will become negative 2 plus 2. So this will be 0, right? Okay. There's an x plus 2 here. Minus 2 plus 2, it will be 0. So the multiplier of A will be 0 and the multiplier of B will be 0 and we could compute for C. Right? So when x equal to negative 2, this portion here will become 0, this portion here will become 0 and we could compute for C. But we must have to substitute or plug in the value of x to the given equation. So 3 times minus 2 equal to 0 plus C. When x is equal to negative 2, this will be negative 2 minus 1. This is negative 2, negative 1. Or it seems this is gone, right? This is minus 6. Minus 2 minus 1 is minus 3c. They are both negative. We divide both sides by negative 3. So the value of c will be equal to 2. As simple as that one. Okay, you got it, guys? Same as from the previous lesson, number 86. That is, we assume a certain value, so we could eliminate the other two. We could compute for one value from the unknowns. Okay, next. When x is equal to 1, this is 1 minus 1, right? Am I still on camera? So when x is equal to 1, the multiplier of b will be 0. So b will be 0. Even c, this will become 1 minus 1. The multiplier of coefficient c will be 0. So actually, when x is equal to 1, we eliminate b, we eliminate c, we could compute for a. But we must have to plug in the value of x equal to 1 to this given equation. So this is 3 times 1 equal to a. This will become 1 plus 2, that will be 3 squared, B now will be 0 because this is 1 minus 1, right? It will be 0, C will be 0, or this is gone. So actually, we could compute for A. A now will be 3 over 3 square, or that is 1/3. Right? So we now know the value of C. We now know the value of A. Okay? We could either use this equation here. Actually, we can substitute the value A to this equation, the value of C to this equation, and we could compute for B. Right? When x is equal to 0, okay, we put x equal to 0. We are not violating anything. When x is equal to 0 to this equation here, okay, the left hand side will be 3 times 0. The value of A is 1/3. Right? I'm following this. I am now substituting the computed value of A. So this is 1/3. When x is 0, this will become 0 plus 2, so it will be 2 square. Okay? Next one, B. When x is 0, this will become 0 minus 1, this is minus 1. 0 plus 2, that will be plus 2. All multiplication, right? Plus the value C. But what is C? We now know the value C. C is actually 2. We computed it, right? So when x is 0, this will become 0 minus 1, so this is times minus 1. Okay, so after the substitution of x equal to 0 and the value of A equal to 1/3 and C equal to 2, the only unknown is actually B. Right? So simplifying this one, 3 times 0 will be 0, 1/3 times 4, that will be 4 over 9. A minus 1 plus 2 will be minus 2 times B, that will be minus 2B. 2 times minus 1 will be minus 2. Right? So what's next? I will put this one on the left. It will now be plus. We maintain 4 over 9. Right? This is minus 2. But this is minus 2 is very dangerous because it got no 9 underneath. So we must have to multiply this negative 2 by 9 over 9. So it will be similar to this 4 over 9. So 2b will be equal to 4 over 9. 2 times 9 will be minus 18 over 9. And this one here, it's coming out from the short videos. We are adding two fractions with the same denominator. So we'll just add up the numerator all over the same denominator, right? So 4 minus 18 will be negative 14 over 9. So b now will be equal to, actually these two here cancel with this. 14, it's divisible by 2, that will be 7. So the value of b will be negative 7 over 9. Okay? So the equivalent partial fraction of the given algebraic expression 3x over x minus 1 all over times the product of x plus 2 quantity square equal to, I will just follow this one because we now know the value of A, we now know the value of B, and we now know the value of C. We call that direct substitution solution. So the given algebraic expression will be equal to A. What is A? 1/3, this is 1/3 over x minus 1. What's the value of B? B is negative 7 over 9. I'm following this. Over x plus 2. And what is the value of C? C is actually 2, right? So this is 2 all over x plus 2 quantity square. Okay? So this looks very nice. If you are under the study of integral calculus, your professor put this one an integral sign and it places a dx over here. To integrate this one, it's complicated without knowing partial fraction. So after taking the equivalent, you could take the integral of the left hand side, right hand side, the integral of the right hand side, you just add up the x over here. Okay? And this all falls under, this is natural logarithm, this is natural logarithm, this is under power formula. So the complicated algebraic expression, if you are under the study of integral calculus, to integrate this one, we must have to take the equivalent partial fraction. That's why our topic for this morning is partial fraction, repeated linear factors. Okay, that's it guys. This is a good example for partial fraction involving repeated linear factors. Okay, good morning from Los Angeles, Professor David J.